Okay, PS5 is it 5? Yeah, PS5 is coming due. Any questions about that? Any problems? Yes?
I'm a little confused as to what 5-2 is asking for exactly. Like, I guess I'm a little lost on what the decision tree is.
Okay, so it's asking you questions about decision trees for two algorithms, 5-2. A decision tree is just a binary tree where every node corresponds to a decision that is made while the algorithm runs.
Okay.
So lots of people have asked for for merge sort, where is how does it work for a recursive algorithm? So let me just show you this. I think the point of confusion is, if you're merge sorting an array, you're going to make two recursive calls to sort arrays half as long, and then more, and so on. So at what point is the first comparison made? Okay, of two data elements. Yeah.
When you're merging?
Okay, when I'm merging. In fact, that's the only place comparisons are made, is when you're merging. But where in this recursion tree here does the first merge occur?
On the bottom?
Yeah, on the bottom down here. Right? So if your array starts out A, B, blah, 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 somewhere down at the bottom you're going to merge the array A with your array B, and the first comparison is going to be of A to B. And so I think people want to somehow think the decision trees look something like the recursion tree, but it doesn't. So the first question is going to be, is A less than B? And the answer is either yes or no. And then we take it from there. If the answer is yes, what's the next comparison? So, and in fact, as long as we're talking about trees that are arrays of a power of 2 length, after that comparison, the second comparison is the same no matter whether the answer is yes or no to the first question. You don't have to actually, once you understand what a decision tree is, you don't have to draw out the tree and count how many vertices are in the longest path. Just figure out what would be the longest branch in the decision tree and what would be the shortest. That's what you have to think about. Any other questions? Okay. I want to tell you what's coming up. So here's a schedule for week 7. We'll be doing modular arithmetic and number theory algorithms leading up to studying RSA encryption. On Thursday, typically, Thursday would have been a continuation of these topics up here. But I'm going to be out of town on Thursday. And so what I'm going to do instead is have TA do the midterm review on Thursday. Normally that would be the following week. So essentially I've switched the midterm review here with this lecture here. So I'll be back on that Tuesday, and so we're doing the midterm review 5 days early. Then the midterm is 2 weeks from today. Okay? Now, I'm not sure that the midterm review will get recorded. It depends on several things. But right here is a link to the midterm review I did last year. So as long as you ignore things about like what day the exam is on and what room it's in and all that stuff, the rest of the review would be the same. I've also got linked into here the last 3 midterms I've given, spring 19, 18, and 17. The review I did last year talked about the midterm from spring 17. TA is going to talk about last year's midterm, and then I got S18 is in there for also. I'll post the solutions after a while, after you get a chance to look at them without the solutions. We're going to just, one other thing is we're going to use 2 rows for the midterm. So if your last name starts with A through J, you're going to be upstairs in I'm going to be upstairs. Let's look at the slide here. There you go. Web 1250. Everybody else will be in here. And you bring one sheet of notes. You don't have to put the master theorem on your notes. I'll print it on the exams. And it'll cover basically through today. PS6 through today. With the possibility there might be some graph topic that spills over slightly to Tuesday. But. Okay, so that's what the next 2 weeks look like. Any questions about that? Yeah?
Can you remind me if we get notes on for the midterm?
Just the one page of notes. Yep, you're right, front and back, printed or handwritten or whatever. Any other questions? Okay, that's not where I want to be. All right, last time we started talking about shortest path algorithms, and we saw that the update operation was the key thing. I said we're going to look at 3 different algorithms. We looked at one, and it sort of indiscriminately updated every edge over and over again. And I put this slide up just to remind you what the update operation is. You update an edge. So you update an edge that starts at U and goes to V and has weight W. And the question you ask is essentially, does this edge give me a shorter way to get to vertex V from the start? So you already know, you've calculated already some distance that V is from the start. And if you go through vertex U, if you go from the start to vertex U and then follow this edge to V, then the cost is going to be distance of U from the start plus W. So if that new distance through U is smaller, that's good, and we update our data structures to remember the fact that, okay, now the distance is known to be smaller, and the parent is known to be different. So that's the key update operation. We'll see several times more today different uses for it. And remember that the Bellman-Ford algorithm that we looked at last time just updated every edge and then updated every edge again. And you keep doing that until either there's a pass where no update, nothing changes when you update, nothing gets updated because we found the solution, or until you've done it V minus 1 times. Either way, you'll be done. Now, we want to look at the special case of a DAG. So I've got a DAG here. We want to find the shortest path tree, and I've highlighted the shortest path tree in yellow. That's nothing we would know before we run the algorithm, but it is the actual answer. And what I observed last time is if you had prior knowledge about which edges were involved in the shortest path tree, then you wouldn't have to worry about the white edges at all. You just have to update the yellow edges, and you'd get the right answer. The white edges don't matter. Any time you spend updating the white edges is a waste of time. Now, you can't get away without updating them, but in principle, you could ignore them. And what's the proper order to update the edges? What's the perfect order for updating the edges? Yeah.
Topological.
Okay, in a DAG, it's in topological order. So you can update the edges out of, if you put this graph in topological order, A would come first, or I guess. So you would update the edges out of A, and then you move to the next vertex and update the edges out of that. And that would give us the perfect order. So for Bellman-Ford, it wasn't a DAG, and we couldn't do a topological sort. So we just flailed around, brute force updating all edges over and over again. But with the DAG, it's more straightforward. You can linearize the DAG and then update the edges out of each one. So here's a possible linearization. I, A, B, C, D, H. GFE. So we would first do those two useless updates out of I. We don't know they're useless, but we would update them. And next we would do the edges out of A, and then B, and then C, and so on. And you also remember last time that I said that on an arbitrary graph, the right order to update is you want to update all the edges that lead from the start vertex to all the yellow edges that leave the start vertex to a vertex that's one hop away, one edge away. Then you update the ones that are 2 edges away. And then you update the ones that are 3 edges away. That would be F and D, and so on. As long as you respect that order, you're good. As long as you update an edge after you've updated all the edges that come into its vertex, you're fine. So are we doing that here by doing the topological order, the linearized order? Yeah, linearization does that for us. Just do the topological sort, and we're guaranteed to get the edges out that lead into B before we look at the yellow edge that leads out of B. So how much work is this? What's the complexity of updating this way? Yep. Okay. It's linear, as you might expect. There's, given that, so given this ordering here, this is a possible order in which the edges are considered. And I've highlighted the ones that matter, the yellow ones, and you'll see that they respect the tree. AB comes first, and then BC, and then CD and CG follow, and so on. Okay, we have to linearize the graph. That's linear, cost of enumerating the edges, and we have to update each edge. Okay, we don't just update the yellow edge; we update each edge. But the update operation is constant time. So what would be the cost of updating every edge? Yeah, that's just, you have to find the edges, so cost of enumerating the edges again. And that's just v squared or v plus e, so it's linear in terms of the size of the graph representation. And you remember that, say on a matrix, Bellman-Ford was v cubed. So that's because we had to update each edge over and over again, but on the DAG we don't have to do that. So another example of where topological sort wins when you design an algorithm on a DAG. Right, so that's the simplest of our 3 algorithms. Well, I don't know, maybe Bellman-Ford is simple too. Right, any questions I can answer about that before I move on? Okay, yeah.
So I was curious, what context can you not use this algorithm? It would be like if it had a cycle.
Yeah, right, if the graph has a cycle, then it's not a DAG and you can't use it. Okay. Now you remember that for Bellman-Ford, all we assumed was no cycles of net negative costs. So you could have negative edges, but you just couldn't have cycles where if you go around it, it's a negative distance, because you can go around it many, many times and make the path distance as low as you want. So that was one assumption, one extreme, I guess. The other extreme was DAG. We assumed no cycles at all. So this case in between happens fairly commonly in practice, where there are cycles with no negative edges. So here's our graph here, and the idea, this is going to lead up to Dijkstra's algorithm, which you've seen before in 2420. We're going to, Dijkstra's algorithm is almost a twin to breadth first search. And in particular, it grows the tree incrementally, beginning at the start vertex and growing out. Initially, the tree contains only the start vertex A, and that was true for breadth first search as well. During each pass, we're going to figure out which of the non-tree vertices that we've discovered is closest to the start vertex and add it to the tree. That's exactly what breadth first search did. It just used a different notion of closest. Breadth first search was just counting edges. We're adding up weights. So there you have the first vertex in the tree is the start vertex, and at any given time we've discovered these purple ones, And we've got to figure out which of these is closest to A. Now, it's easy to see which of these is closest to A because they all have edges to them directly. So the 2, the 3, and the 4, there's the 2. So the first thing we're going to do is incorporate the B into the tree. And now our fringe has changed. So now we're trying to figure out which purple one is closest to A. And which is it? Sort of have to look. They haven't told you how to do it yet, but C is 3 away and E is 3 away. So either one of those would work. Okay, now which is closest? E. Now which one? See, F is 4. D is 4 as well. Yeah, G is longer. So I put D in, and then F. And now G is 5. I believe H is longer. No, I guess H is 5 too. And then G. All right, now, where do we take advantage of the fact that there are no negative edges? It's not obvious from this. Yeah?
If there's a negative edge, then I know that it has more edges to it. Could be a shorter distance.
Okay. Let's go back, and for some reason this isn't letting me go back. Let's just restart this here. Okay, here's the property of this algorithm we're going to take advantage of. When a vertex becomes yellow, once we found the shortest, the thing closest to the fringe vertex closest to the start, it never turns purple again. Once it turns yellow, we are certain we have found the shortest path. So how do I know? Just because, basically, we're just looking at the edges from A to those 3 vertices right now. And we see there's an edge of weight 2, and we say, okay, that is absolutely the shortest path to B. We will never find the shortest path. It's okay to commit to it. Now, there could be a shorter path to E, or to F. What weight could you put on that edge from B to F such that there's actually a shorter path from A to F than on weight 4? Make it like a half, right? So you would have, or 1. And if this edge right here had a weight of 1, then okay, this is absolutely the shortest. But then in discovering B and putting B and then finding the shorter path to F, this wouldn't end up being the path to F we would take. This would. But nevertheless, we're never going to find a shorter way to get to F. What can we change about this graph so that they're actually, even after we turn B yellow, there's no shorter way to get to it? I'm sorry, there is a shorter way to get to it. Yep.
If say like F was pointing to B instead of the other way around, and the weight from F to B was -10.
Okay, right.
Find a shorter path.
Right. Just imagine we took this edge here and flipped it around so it went from F to B, and we gave it a weight of -10. So from the vantage point of A, just looking at the fringe, we would say the shortest path from A to B is this one. But then later on, when we turn to F yellow, we will discover a shorter path to B than we had discovered originally. And we sort of have to turn F back to purple. But it's a property of Dijkstra's algorithm that once we found the shortest path, it's guaranteed to be the shortest path. So if you allow negative edges, that assumption goes away, and the algorithm doesn't perform. Now, the key question is, how do you keep track of which vertex to go to next? And it involves using priority queues. So for a priority queue, these are the fundamental operations we're going to be using. Imagine it's like a queue in that it contains elements, but the difference is each element has a weight. Each key has a weight. And at any given time, we don't want to get out when we get an element out of a priority queue, we don't get the element that's been in there the longest. We get out the one that has the lowest weight, even if it was inserted recently. So we're going to have these operations. We're going to be able to construct a priority queue that has room for n vertices. We're going to be able to test if a priority queue is empty. We are going to have a method that will take something like V, which would be a key, a vertex, and W, which is a weight, and insert it to the priority queue such that V has that weight. And that will either insert it if it's not there already, or update it, change its weight if it's already in there. And then we're going to have an operation to remove and return the key with the smallest weight from the priority queue. Now, you must have in 2420 studied a way to implement this interface, this abstraction. What was it?
Red-black tree?
No, red-black tree is a kind of a binary search tree. This doesn't describe a binary search tree. Yeah.
With a heap?
Yeah, with the binary heap. And here's Dijkstra's algorithm, just as a preview. We'll delve into it in more detail. I put it here so you can look at how similar it is to breadth-first search. So look at the beginning. This stuff here is exactly the same. So it uses the same distance array, the same previous array, initializes it the same way. Now, this illustrates one way where Dijkstra's algorithm assumes there are no negative edges. We say the distance from the start vertex to itself is 0. If there were a negative edge, from the vertex to itself, I guess that would be a negative loop, which is bad. Anyway, if there were a negative edge from the thing to itself, the shortest distance wouldn't be 0. It would be really negative infinity. So that's not going to happen. We're not allowing, and none of these algorithms allow negative loops. Anyway, we set up the data structures the same way. Then we come to these two statements here. We over in breadth-first search, we created a queue and then added S to the queue. Here, we're creating a priority queue and adding S to the queue with the weight of 0. Same structure. Then we have the loop. While the queue or priority queue is empty, we get an element out of the queue or the priority queue. We find all the edges out of that element, and then we update if necessary. The test is a little bit different. On breadth-first search, we update things if the known distance to V is infinity. Over here, we update the edge if we found a shorter way to get to V. And then, in addition to updating distance and previous, we add something to the queue. So it's sort of line for line, very similar. The only difference is, the two differences are we're involved with edge weights, and the second is we're using a priority queue instead of a queue. Otherwise, if you understand breadth-first search, it's pretty easy to understand Dijkstra's algorithm. So let's look at it in more detail. All right, so this is the same slide we just looked at, so I won't stop there. We're going to animate it. We're going to go through it and watch how it deals with that graph right there. So first we have to initialize our data structure, which I'll do here. So you've seen that before. That's just same as breadth-first search. The distance of A is initially 0. The distance of everything else is initially infinity. We don't know anything about previous. Now we have to create an empty priority queue and stick S on it with a weight of 0. And we do that, but this little gauge down at the bottom is blocking it. Okay. So there's our priority queue. I colored A initially. When things go onto the priority queue, I'm going to color them purple. And you can see the priority queue at the bottom. It says A has a weight of 0. Now we just loop through the priority queue, pulling things out, and then we update all the edges based on what we pull out. So what are we going to pull out? The only thing is A. So we'll move it from the queue. When it comes out of the queue, I'm going to call it yellow, and once it turns yellow, it'll never go back on the queue because of this negative edge restriction. So there we have it. We're going to look at all the edges that leave A and go somewhere. So in particular, we'll look at that one right there. What happens with that edge? The edge from A to B of weight 2. So in this case, V is B, U is A, W is 2. Have we found a shorter way to get to B than the infinity that we started with? Yes. So we do the update. Because the known distance to V is infinity, we just found a way of cost 2. So we need to do the update. So we're going to change, when I click, you're going to see distance of B change. So this distance will change to 2. This previous will turn to A, and what else will happen? B will go into the party queue. So there it goes. So B has been updated, and the purple thing, I've turned it purple and put it on the queue. Now what will happen next? We just went through, we found one edge out of A and dealt with it. What happens next? Next edge out. So we'll do that edge to E out. And it's also a better way to get to E. And so when we update it, you're going to see the information for E change, and E goes on the queue. And then we do the same thing for F. We found a better way out of F, or to F, and so it goes on the queue. So far, I mean, this has happened in breadth first search as well. You just want to see the weights. Okay. So we're certain about A. We found the shortest way to get to A. That's 0. Now we're going to take the thing with the smallest weight out of the priority queue, and that will be frozen then as well. So we take out B. B has the smallest weight, so I'll pull it out, and we'll turn it yellow because now we're certain about it. Because there are no negative edges. We know we're not going to wander down here and then find some negative edge that leads back to B that's a win. Okay, so what happens now? You start looking at the edges out of B. So we'll do that one first. Current known distance to C is infinite, so we're going to update the information we have about C. So, oh, there we go. So C goes on the queue. Now that edge right there. Now, the current known distance to F is 4. Is this a better way? Let's see. B is 2. The distance to B is 2. And add 1. The edge is the way to 1. So that's 3. 3 is better than 4. So what's going to change here? Let's see. The information for F is going to change. The parent will change to B. The distance will change to 3. And one other thing changes. Right, the priority queue gets updated as well. So the weight of F will change to 3. So there it is. So F's weight inside the priority queue changed, and also in the distance array. And I believe that's all the edges out of B. So what happens now? What comes out of the queue this time? C could come out, or F. They're equally small. I chose C. We make it yellow. We look at the edge out from C to D, weight 1. That's better than infinity we know about, so we do that update. We'll consider that to G. Every time it goes to a white vertex we've never seen before, it's going to get changed right away. So D and G both went on to the queue with their new weights. Remember, these weights are distances back to the start. Okay, now what comes off the queue? F is the smallest, so F will become yellow over here. And we've got a couple edges to consider. There's that edge from F to C. So let's see, F has a distance of 3, and this with this edge, that gives us a path of length 7 to C. Is that better or worse than what we know about? Worse, so no update happens. Then we got that one from F to E. That will be a path of length 5 to get to E, as opposed to the 6 we know about right now. Yep.
Isn't it 4 because F's parent is?
Oh, I'm not. You're right. You're right. It's 4. Yeah, F's. Thank you for pointing that out. F's distance is 3. I was thinking 4. So F's distance is 3. We add 1 to it, we get 4. Either way, it's better than 6. So you'll see the information for E get updated, both in our arrays and in the queue. So E changes to 4 here, and E changes to that right there. And that's all the edges. Now we'll take the smallest out. It's either D or E. I chose D. We're going to update the edge to that white edge, which is going to a white vertex, which is going to put it onto the queue for the first time. That's all the edges out of that. Let's see. We got to pull E out. There are no edges out of E, so nothing to do. We're going to pull either H or G out. I took G. We got to update that edge, and is that going to change anything? Let's see. G here, it says 5. That will be something of length 7 to H, and currently H is 5, so that's not going to improve anything. So nothing gets updated. And then finally, H comes off the queue, no edges out, and so nothing. We're done. The queue is empty. We dealt with everything we can reach from A. We never saw I because there's no way to get there from A. Okay, so that's Dijkstra's algorithm. Hopefully you see the similarities to breadth first search. The version that I gave you is different from the one in the book. It's just organized differently, and I do it that way to highlight the similarities between the two algorithms. Yeah, any questions I can answer about it? And remember again, we got this property that once a vertex comes off the queue and I turn it yellow, it's never going back on the queue. And that's because of that negative edge restriction. It turns out, if you allow negative edges, Dijkstra's algorithm will still work. So, if that's the case, why do I say don't use negative edges? Yeah?
If you don't use negative edges, well, at that point, will you no longer find the shortest path? You'll just find a short path?
No, it'll find shortest paths. The way I've written the code here, what would happen is, with negative edges, the vertices would be turned from purple and put back on, would be turned back purple and put on the queue. Yeah.
Is it because you wouldn't need a priority queue, so that's kind of wasting time?
Well, no, you'd still need a priority queue. We won't change anything about the algorithm. Yeah.
Does it just make it take forever?
Right. It just makes it removes. It's no longer an efficient algorithm. With negative edges, it can take exponential time. Okay. So in a sense, it works, but then you can't guarantee how long it'll take. Okay, so to keep the performance guarantee, we need to, that's a negative edge restriction. So basically it becomes worse than Bellman Ford. But I didn't give a performance guarantee, so let's think about that. Now we've already analyzed depth first search and breadth first search. This analysis is going to be very similar. The main difference is going to be, in fact, I think the only difference is going to be, with breadth first search, adding to the queue was constant time. Removing from the queue was constant time. With the priority queue, that's not the case. And so some of the operations become more expensive. So we got this initialization block right here. And as always, that's just O of V. We're just initializing arrays of length V. There's creating the priority queue. That's one of our priority queue operations. And I don't know, let's call that O of create. We'll come back to that. Whatever it costs to create, that's what it is. We have to add a key to the priority queue, and I'm going to call that O of insert. We'll come back and worry about that later. We got to do that loop test V times at most, once for each vertex. Notice if we had negative edges, we couldn't make that. We could do this test more than v times because if things going back on the cube. So that's going to be v times. We're going to pay the cost of of testing whether the cube is empty, whatever that costs. We're going to remove v times. We're going to remove the smallest element from the cube. So I'm going to call that v times delete, whatever the cost of delete is. We're going to have to enumerate the edges as always, and then over the course of the entire algorithm, we're going to look at every edge once. So we're going to do that test right there, e times. And at most, these two statements here are going to be executed e times. So all this is constant time done e times, and also we got to do this insert e times. Anyway, that's the accounting for it. The key things are we end up deleting from the queue v times, and we end up inserting to the queue e times at most, inserting or updating. And in our case, in the case of the regular breadth first search, delete and insert were constant time, and these aren't. Otherwise, that's the same analysis we saw for breadth first search. So here's what we came up with. Now I've simplified a little bit. Like I didn't include the O of v because it's smaller than v times empty, and I didn't include O of create. I didn't create this O of insert. I don't have because I already have an e times insert there. So these are just the dominating terms. And you'll see it depends on the cost of various things in the queue. So it depends on how we represent our priority queue. Now, we're going to look at different ways of representing the priority queue, but surely we could create a queue, an empty queue in O of v time. And surely we could find a way to test if the queue is empty in constant time just by keeping a flag around to tell us if it's empty or not. So if that's the case, then the O of create term is smaller than v times empty, or O of create and O of v times empty are smaller than some of these other terms. So it simplifies to that. So it just comes down to v deletes and e inserts plus the cost of enumerating the edges, and that depends on what kind of data structure. If it's a matrix, then we got O of v squared. And I say hopefully we can find a way to do insert in constant time and delete in linear time, now, or in O of v time. Why do I hope for that? What's my thinking behind that statement? Why don't I wish for constant time for both? Yeah.
Well, for delete, you have to go through all of them to find the lowest value.
Okay, so you're making. Okay, so you're thinking about the representation and coming up with that. I'm not thinking about how I would represent the data structure. I'm trying to minimize this complexity measure. Yeah.
Is it because E can be greater than V?
Well, we know E can be better than V, but what would it take to make this no bigger than possible? What's the smallest this sum could possibly be? V squared. Can't be any smaller than O of V squared. So if delete can be as big as O of V, and this thing here turns into O of V squared. I'm trying to keep this term, V times delete, and this term, E times insert, to be V squared or smaller, because I want a V squared algorithm. So I hope that delete is no worse than O of V, so that becomes a V squared term. And why do I hope insert is constant time? Because E is no bigger than V squared. And so that would make that a V squared term as well. So good. So if we could design a priority queue that had those two properties right there, we would that would be the best design of a priority queue for use with a adjacency matrix. Now, what about adjacency list? Let's play the same game. I wish that we could have complexity no worse than E plus B. That's what I would like. So what properties would delete and insert have to have? The complexities would delete and insert have to have in order for this to be the case. They both have to be constant. It turns out that's too much to hope for.
Shocking.
It's theoretically impossible to have a priority queue, a comparison-based priority queue, that are that fast. And the reason is, if it were possible, you could use a priority queue to implement a sort that ran in linear time, a comparison-based sort that ran in linear time. Think about it. You've got an array of numbers. You could just add them all to the queue. That would take O of V. If you have n elements, that would take O of n time. If we assume that insert is constant time. Once they're all in the queue, what do? Just delete min them out. They come out in sorted order. And if we assume delete min is constant time, that would be O of n as well. So that's called heap sort. And we know that comparison-based sorting can't run in linear time. So that implies that you can't have a priority queue that's that much, that good. So we can't wish for that. So instead, I'm going to wish for sort of the next best thing. I'm going to hope that they're both log v or smaller. Because if we can get it that small, then it's okay. It's close. It's e plus v log v. And that turns out to be the complexity of Dijkstra's algorithm on an adjacency list. So it just boils down to now we've got to figure out how to get these two representations. One representation of a priority queue designed for use with the JC matrix, where we want one set of properties, and the other, which is a binary heap, for use with the adjacency list. So let's take a break and we'll see about these representations. All right, I was asked during the break a question. I'm always asked, but not always during the break. So I'll answer it for everybody here. The idea is, could you not take a graph with negative edges and then just add the same amount to each edge to make them all positive, and then run Dijkstra's algorithm and get the same answer? Deal with the negative edges that way. And we've already worked out the answer up there. So here, suppose we had this situation. Okay, so we got that graph right there. We can't run Dijkstra's algorithm on it, or we're not running Dijkstra's algorithm on it because they're negative. Could we not turn this into all the edges positive by adding 1.5 to each edge? Run the algorithm, find the shortest path, and then that same path would be the answer to the original graph. Okay, so what happens if we add 1.5 to each edge to make them non-negative? Well, first of all, what's the shortest path? Right, this, I'm going to highlight the shortest path. The path is of weight -2. So suppose we decide to add 1.5 to each vertex to make them all non-negative, to each edge to make it non-negative. You end up with an edge of 0.5, you end up with basically a 1/2, a 1/2, and a 0. Now what happens when you run the algorithm? It finds this path right here, which isn't the one we want to find. So this trick of converting all the negative edges into positive ones doesn't help in every case. The reason is, if we could find a way to add a constant amount to each path, would be good. But we're adding a constant amount to each edge. So we're handicapping short paths that have many edges relative to longer paths that have a few edges. So that occurs to a lot of people, but it just doesn't work. Okay. So here's our priority queue. Those are our operations we talked about before. Here's, and what I'm going to propose that we do is just represent a very simple priority queue. We will just have an array indexed by vertex. Think of it would be a map if the vertices weren't integers, where we store the weight. So this priority queue contains A, B, and E with weights of 2, 5, and 3 respectively, and then the rest of the elements aren't in there. So let's see how it works. Let's say we want to insert F with a weight of 4. How would you do that? What has to change about the data structure? Yep.
Go to where F is in the array and just change that value to 4.
Right, so we go to index F, and we're assuming that these vertices names are either indexes or we're just using a hash map. But we can go straight to here and we store 4 right there. Boom. It's in the queue. How long did that take? What's the complexity of that? That's constant. So we got our constant time update going. Insert or updates constant time. What about B? Insert or change B to 1. Go to B, change the 5 to a 1. Constant time. Delete min. Okay, what's the delete min going to cost? Yeah, we got to scan through the array and find the smallest one. It's that one right there. So we basically we'll turn that to a null and we return the B. Okay, then we do H. It goes in like that, and another delete min takes another scan, and we find A. Okay, so linear time for one, constant time for the other. So creating the priority queue takes linear time to initialize the memory. Insertion, constant time. The test for empty, I mean, the way I've written it, to test for empty, we'd have to scan and make sure that there are no they're all nulls, but we could store a bit somewhere, keep track of that, and then delete min is linear time, which is what we wanted to make our Dijkstra's algorithm own an adjacency matrix as fast as possible. Now, what's ironic about this? Yeah? No? Yeah?
That is an adjacency matrix implementation. It's the same idea.
Well, yeah, he's saying it looks sort of like an adjacency. Yeah. Looks like in a row in a JC matrix. Okay, you studied, a slicker implementation of priority queue in 2420. Why don't we just use that? Just log V for both operations. You didn't have this linear time delete min. Why not just use it?
Because for what we said, we need delete to be constant, not log
Yeah.
V.
To achieve that V squared bound, we need to use a crappier priority queue. Basically, that's what's ironic about it. If we used a binary heap for this version of the algorithm, the cost would not be V squared, it would be V squared log V. The limiting thing is, we can make the delete min faster with a binary heap, but that makes the insert slower. It makes it a log V, and that's the thing we're trying to minimize. Since we're doing with a JC matrix, we're doing V squared inserts at most, and or at least if it's a dense graph, we're doing V squared inserts, and if they cost log V, the algorithm becomes worse. So we need this, dense graph, a JC matrix. We need to use this form of priority queue, which is simpler to understand, not as fast for general use, but exactly what we need here. Now, in the other case, we need to work a little bit harder and come up with binary heaps. So let's remember how they work. So remember, a binary heap is, first of all, it's not a binary search tree. It's shaped the same. It's a complete binary tree, though. What does it mean, complete binary tree? Yeah.
Every level except the last one is completely full.
Right. Every level except possibly the last one is completely full. And furthermore, on the last level, everything is pushed over to the left. All the holes are to the right. So if there's only one thing on the bottom level, it would have to be this one. Okay? That's a complete binary tree. The elements the vertices contain elements that can be compared to each other. And a child's parent is no smaller than its parent. So the 2 is bigger than the 5 and the 2. The 5 is bigger than the 6 or the 8. So that's the heap condition. Now here's the insertion method. The basic idea, let's look at inserting 1. What you do is you're adding something, so you just stick it in the next spot on the bottom level. So we're filling in the bottom level from the left, so the 1 will go here. And then we just push it toward the root as far as it'll go. You compare it to its parent. If this 1 is smaller than its parent, you need to swap them. It is. And same thing happens here. Smaller, you swap it. So you just have to push it toward the root. Let's insert a 4. Why did it go there?
That's the next open spot.
Right? That's the next open spot. And now we push the 4 towards the root. 4 and 6, swap them. 4 and 5, swap them. 4 and 1, don't swap them. Done. So that's the insert. So if there are n things in the tree, what's the complexity of an insert? What's the worst case? Log n, because that's the depth of the tree. The worst you can do is push it to the root. You don't have to look at most of the elements. Okay. Then there is deletion. So let's suppose we want to do a delete min. Okay, now it's easy to find the minimum element. It's sitting at the root. But if we just get rid of it, we've split the tree into 2 pieces. That's no good. So what we do is, when we shrink the tree by 1, this is the vertex we want to go away to maintain the complete tree. So we just remove this vertex and put the 6 up here in place of the 1. And now what do?
We push the 6 down.
We try to move the 6 down. So we have to compare the 6 to its 2 children, and we swap it with the smaller of the 2, assuming it's bigger than either one. So we compare the 6 to the 4 and the 2. The 2 is the smallest, and it's smaller than the 6, so we swap. Then we do the same comparison. 6, 9, 3. There's the 6, there's the 3. We swap them, and we're back into a good condition. Do it again, what's going to happen?
Swap the 2 and the 6.
Right? The 6 this vertex goes away, the 6 will go up there, right there, and then we just push it down. We compare the 6 and the 3 and the 4. The 3 is smallest, so we do the swap. Compare the 6 and the 9, and there's nothing else. The 6 is smaller, so no swapping done. And again, that's also log n, because the worst we can do is push from the root to the leaf. So both operations are log n. Okay? That all makes sense? What about changing an element? What if I said, okay, I want to change the weight of 4 to be 1. I want to change what's stored in that vertex 4 to be 1. Yeah?
Would it just be removing the 4 and then adding in the 1?
Well, yeah. Well, basically, you could take the 1 and if you could go to where that 4 is, you could replace the 4 with a 1, and then either push it toward the root or push it toward the leaves, depending on the relative size of those two. The problem is finding the 4, because there's no efficient way. We don't want to have to go search through every vertex to find the thing we're looking for, because that could take linear time. So we need to find a solution for that. So we got to find it. So the reason this works, the reason finding works. So in reality, there are two things in each vertex. There is the key, which is B or A or F, and then its weight. The previous diagram, I'll just show you weights. You can take a complete binary tree and represent it compactly as an array. Just do it in level order. So you see, we take the first level, and that's the first thing in the array. I'm using a one indexed array just because it makes things slightly simpler. So the root of the tree goes here. The next level, the A and the C come here, and then we have the third level, E, F, D, H, and then G. Right? So you can pack a binary tree into an array like that. The root index is at 1. If you want to know the left child of this thing, you just double that. So we're at index 3, so its left child is at 6, and its right child is at 3 times 2 plus 1, which is 7. If you want to know the parent of this one, you divide it by 2. It's at index 8, divide it by 2, you get there. Index 3, divide it by 2, discard the remainder, you get there. So when doing a binary heap, we don't bother with that data structure, we just use an array. Now, why don't we use arrays like that for all binary trees? Why don't we use them for binary search trees? Yes?
If it's unbalanced, you have a ton of empty space.
Right. If it's unbalanced, you have a ton of empty space. So imagine a binary stick. You end up with like 2 to the n linked array to hold the n elements, where most of them are null. So it's no good. It works here nicely because the tree is complete. Okay, now. Something's not working. The mouse is not working.
Oh no.
No, that's not working either. This thing's loading again. All right, I can touch the screen. That's good. Now, imagine if I wanted to look at that array and suppose I want to do the operation of changing E's weight. Ignore the array that I displayed at the bottom. What would it take to change E's weight? Or to find E? Is there anything better than just you'd have to scan the array looking for the cell that contains E? And that's linear time. We want that. We want that to be logarithmic time.
You could jump through the tree, right? Because if you know, like,
We don't
Y
know
is
where.
there,
But see, we don't know where E is.
do we know its weight?
Yeah. No, not necessarily.
No.
We just know E is in there, and we don't know where. So we would have to scan through looking at the keys trying to find E. Yeah.
Can you like jump to the half point of the array? Use the
Well,
cell and then, like,
would a binary search work?
uh,
Probably it's not ordered. It's not a sorted array. It's certainly not sorted by key. So yeah, that's not going to help. So my solution is to create a parallel array down here. And the idea is this array contains the index, so that this says B is stored in that array at index 1. So to find E, you come to index E, see the 4, go to index 4, there's the E. These parallel arrays. That's what makes the update fast. So, so let's do a delete min. I'm going to. This is a complicated animation. Let's see the first step. So to do the delete min, we have to swap the, get rid of the one vertex and stick the information in the root. What's going to change about these two data structures when I do that? So this entry over here, the 6/G should become null, right? 6/G should show up here. What's going to change down here?
G will be turned to
G will turn to 1, and B ought to become null or something, because it's not even. Notice this, and I'll be done quickly. When you're about to move G, you go, oh, before I'm moving it to vertex to index 1, I'm moving G, so you come down here and change it to 1. You can use this as an index down here, just like you use this as an index up here. So you have to update both operations anytime things move. So we do the swap, and you see what happened. The tree changed. I'm just showing you the tree just to illustrate the array. The array reflects the tree, it changed, and the array of indexes changed because things were rearranged. So as we do things, now we have to push down towards the root. When we do the swap, it's reflected in both arrays. When we do that, it's reflected in both arrays. So any operation involves constant time updates to both of these arrays down here. We don't never have to search to find anything. All right, now let's change the weight of E to 3. So we have to first use E as an index to the bottom array. We find out E is at index 4. We go to index 4, and then we can work on it. And we're supposed to change its weight to 3. So we change it to 3. And now we have to push it toward the root, which is going to involve changes to both arrays. And we're done. So that parallel array is what makes that update fast. We have to pay the price of keeping the parallel array updated every time we move things, but that's no big deal. Okay? So that's Dijkstra's algorithm priority queues. I want to briefly talk about heap sort. The idea behind heap sort is you take an array of elements and convert it into a heap. Actually, we're going to do a max heap instead of a min heap. Turns out that you can do that without doing any copying. You can convert it into a binary heap in place. You can take the array that contains the elements, convert them into a heap in the same array. Then you just do a series of delete max operations. Now, as your heap shrinks, it's going to open up room on the right side of the array. So when you delete the max element from the heap, shrinking the heap by 1, you stick the max element in the newly vacated space in the array. And as a result, the heap shrinks and the sorted portion grows. It's much easier to see that with an animation. I can dig it up here. Okay, I'm going to run a heap sort in slow motion for you. So notice, what is this structure here? That's your max heap. So up there is the root. It's stored in an array. So there's the root element, and it's the biggest one. The next two elements, it's not a perfect line, but you can sort of see that you got the big elements at the root and the smaller elements toward the leaves. And just repeatedly does a delete max. And that shrinks the heap and stores the element in the vacated spot. And so as the heap shrinks, the sorted array grows. So the heap is sort of reducing itself toward the corner, leaving behind the sorted array. That's heap sort. Here's the same thing if you start with a sorted array. This is the weird thing about heap sort. Look what it does. Why did it do all that mess?
Because it has to turn it into a heap.
Right, it's taking the sorted array, turning it into a heap, which sort of almost reverse sorts it, puts things on the wrong end, and then rebuilds the heap. And while I'm at it, if we do, no, I want the order to be descending. Let's see what happens here. So when it started, it was a heap. So it's initially it is a heap when it's in descending order. Okay. All right, that finishes up chapter 4. We are going to spend the next 15 minutes starting chapter 1. Okay? Just far enough so that, let me tell you about chapter 1. Chapter 1 starts by talking about modular arithmetic. So we're going to talk about that today. And then it builds a series of algorithms that deal with integers. So sort of the study of the property of integers is called number theory. So these are number theory algorithms. And what we're doing is we're building blocks that we need to understand how RSA encryption works. So RSA encryption, public key encryption, is what makes e-commerce work. So we'll be sort of looking at the details of how everything works. So here's a question for you. What is x mod n? Now we're going to assume that x and n are integers and n is positive. So when I ask you, what is x mod n, what am I asking?
What the remainder of x divided by n is?
Okay, he said, what's the remainder when you divide x by n? Right? That's one way of looking at it. That's perfectly good unless you're talking about negative x's. We'll worry about that later. That's another way of thinking about it. X mod n. Okay? Well, so here's the formal definition. X mod n is x plus kn, where k is an integer and that sum is between 0 and n. That takes care of, so it doesn't talk about remainders. It talks about adding or subtracting n to get the sum or the difference with x into a proper range. So we want to add a multiple of n to x to get it into the right range. So with that definition, what is 4 mod 5? What can you add to 4 in order to make the sum? What multiple of n do you add to 4 to get it between 0 and 5? Yeah, you don't have to add anything. It's already in the right range. So 4 plus 0 times 5 is 4. So 4 mod 5 is 4. What is 14 mod 8? 6. So the idea is if 14 is bigger than the modulus, or greater than or equal to the modulus, you just subtract the modulus over and over again until you get something smaller than the modulus. What if it's negative? What if your x is negative? You add multiples. Okay? So 14 mod 8, you subtract 8 from 14, you get 6. That's in the right range, so that's your answer. Another way of thinking about it is you divide 14 by 8 and the remainder is 6. That's perfectly fine. That's same deal. 101 mod 4. 101 divided by 4 is something, but we know the remainder is 1. 25 remainder 1, right? Okay, negative 14 mod 8. Now you don't do this by just ignoring the negative sign and We know, and then 14 mod 8. So negative 14 mod 8 is not 6. It's 2. Now how do you get that? You add 8 to it, you basically add 16 to it. Okay? So negative 14 plus 8 is negative 6. Add 8 to that, you get 2. That's in the right range, so you stop. So it's 2. Go away. Okay, what about negative 101 mod 4?
3?
Let's see, yeah, it's 3. It turns out that if you take 101 mod 4 and negative 101 mod 4 and add them together, you get the 4. So that's 1, so this should be 3. That was 6, so this should be 2. Okay. Okay, Java and C get it wrong.
What?
And it can, well, I shouldn't say they get it wrong. They don't follow the convention. So if you ask Java what is negative 101 mod 4, it doesn't do negative numbers the way I'm doing them. It doesn't say it is 3. It says it's negative 1. Okay, so if you take the modulus of a negative number in C or Java, you get a negative number. Now, we know I want negative 101 mod 4 to be 3. Why is negative 1 not such a bad answer?
Could you use that before?
What's that?
Is it well, up at the top we have k times n, so would negative 1 just be n minus 1?
Yeah.
Relative to 1?
Yeah. Well, it's n minus 1. The way you would determine what Java gives you an answer or C gives you an answer is take the answer I would give and subtract n from it. So for whatever reason, it wants the answer to be negative. And so negative 101 mod 4 would be 3 minus 4, which is negative 1. It would report negative 1 in Java. It only differs for negative. What would it report for here?
Negative 6.
Instead of 2, it reports negative 6. But what is negative 6 mod 8?
0?
No, negative 6 mod 8 is 2. So the answer it gives is equal in the modular sense to the answer that I wanted to give. It differs by the modulus, basically. Subtract the 2, it differs by the modulus. But it doesn't follow the mathematical convention. And that can be important for one of the caddis problems, when I want the answers to be not negative. So what you have to do is you take the modulus in Java, and then you have to add the modulus to the negative number to get the answer I really want to see. Just a word of warning. Now, we're often going to use this notation. X is equivalent to y mod n. And that just means several things. It means if you take the mod of x, it's the same as the mod of y. It also means that their difference is a multiple of n. It also, that's what it says there. So equivalent. So when it's not parentheses like that, mod is an operator. 8 mod 2 is 0. When it's in parentheses off to the side, then we're just saying it's just a reminder that we're doing equivalence mod n, not in the normal way. So is that true? Is 5 equivalent to 12 mod 7? In other words, if you take the mod of both sides, you get the same thing.
Yes.
Yep. Subtract 7 from 12, you get 5. Or 5 and 12 differ by 7. So that's the same. What about that? Is 14 the same as 36 if you're working mod 3? No. 36 is a multiple of 3, so its modulus is 0. 14 isn't. So, no. What about those?
Yes.
Okay, so you don't want to be running to your calculator for things like this. What's the quick way of saying, yeah, they're the same? They're both even. If you divide an even number, the remainder is 0. Divide an even number by 2, the remainder is 0. So that's easy to see. Okay, what about this? No. the remainder for the first one divided by 10 is 0. The other one, the remainder is 1. So not the same. Modular arithmetic is easy to do than regular arithmetic, and this is why. There are these rules. Basically, what these rules are saying is if you have to do a module, if you've got a 14 times 25 mod 4, there are two ways you can calculate it. You could do it in 14 times 25 and then take it mod 4. The substitution rule says before you do the multiplication, you can take 14 mod 4 and 25 mod 4, then multiply those, and then take the result mod 4 and get the same answer. So that way, you don't have to do large multiplications. So how would you simplify 14 times 24 mod 4? What could you replace the 14 with? 2, and replace the 25 with 1. And 2 times 1 mod 4 is 2. So you do 2 times 1 and then take the result mod 4, you get 2. Okay? Now, that lets you compute things you might not think you could do otherwise. So 2 to the 345th power mod 31. I want to emphasize, this is, when we talk about modular arithmetic, we're talking about integers. We're not interested in real numbers here. These are all integers. The answer is never 1/2. You don't want to see floating point notation when you're doing this. How can we simplify that using the substitution rule? We're allowed, no, how could we rewrite that so we can take advantage of the substitution rule?
2 to the power 5.
What's that?
2 to the power 5.
Okay.
And 2 to the
Right.
power 5.
So what she did was observe, okay, you see this 31 right here. That's 1 less than a power of 2. If you take 32 mod 31, what are you going to get? 1. So rearrange this, realize it's 2 to the 5th power to the 69th power. 5 times 69 is 345. Now what's the substitution rule let you do? It lets you take, this is 2 to the 5th times 2 to the 5th times 2 to the 5th. So you can simplify the things being multiplied. You can't take the mod of the exponent. You can simplify the 2 to the 5th. So that's this rule right here. So what is 2 to the 5th mod 31? 1. Well, I rewrote it as 32 to the 69th power. That's 1 to the 69th power, and the answer for that is just 1. Okay, so that's the substitution rule. If you ever see me give you a problem that involves impossibly large exponents, there's some deal like this going on, where you can simplify things that way. So I just listed all the properties. You've got the usual properties: commutative, associative, distributive. The substitution rule, though, works for modular arithmetic, not for regular. Right, so we got a long way to build from this to public key encryption, but we'll get started with it next week. Okay, bonus.